Hello everyone, we are Team 18 and our project is GeoTrack, a distributed parcel tracking and ETA service. Today the problem we are addressing is very simple. In real logistics systems, millions of parcel scan events happen every single day across the world. Our normal relational database struggles with this scale because of latency and single region bottlenecks. So we designed a fully distributed architecture using Kafka for massive data ingestion, CockroachDB for geo-partition storage, and FastAPI for the APIs and UI layer. As you can see, this is our system architecture. Over here, producers generate scan events, push them into Kafka topics, consumers batch insert them into CockroachDB, and users view the parcel status through our FastAPI, service and UI. Prometheus and Grafana help us monitor the whole system. We also generated synthetic data to simulate logistic workloads. And as you can see, I have started to generate about 10 million scan events right now. We built a Python generator that could do this across 5 global regions with proper location sequences so that the parcel workflow looks realistic. Now let me hand it over to Vineet for Kafka ingestion flow.
Thanks, Bernie. So my part is about how Kafka helps us ingest more than 10 million scan events efficiently. The Kafka layer has 3 main pieces: producers, topics, and consumers. Here you can see our Kafka topics in Red Panda. We have 5 regional topics: AP South, which is Mumbai; AP Southeast, which is Singapore; US East 1, which is North Virginia; US East 2, which is Ohio; and US West, which is Oregon. And each of these topics has 12 partitions each, and it's replicated 3 times. Partitioning helps us distribute the load, and we use the tracking ID of the parcel as the key to maintain ordering for each parcel. Now on the consumer side, each consumer instance polls every 200 milliseconds and take a batch of 300 records at a time. The consumer processes the batch and writes it into the CockroachDB in bulk. It also handles duplicate events using application level idempotency, using the unique constraints and also the on-conflict do nothing queries. As you can see, one set of consumer is already running and processing the scan events data. Right now, each regional topic has only one active consumer instance, so all the partitions inside that topic are mapped to this single consumer. And here you can also see we have our DLQ topic, which will capture any messages that fail during the processing. Now let's talk about scaling. When we increase the number of consumers from 1 to 2 per topic, you can immediately see the partition to instance mapping change in Red Panda. I'll now increase the scale. Here you can see that out of the 12 partitions, all are distributed to the 2 consumer instances, and the mapping has changed here. Thus scaling happened. The load gets distributed and the throughput increases. In our tests, 2 consumers per topic gave around 30,000 events being processed per minute, and with 3 consumers it went up to around 40,000 per minute. I'll stop one consumer instance. Immediately, the Red Panda rebalances and assigns those partitions to the remaining healthy consumers. I'll show you. Yeah, the rebalancing has happened. Even if another instance fails, Kafka still continues processing, maintaining availability. Another important thing is, if the consumer dies while processing a batch, the messages are not lost because the commits happen only after successful writes. As soon as we restart the consumer, it continues from the correct offset. This demonstrates how Kafka maintains high availability and strong durability even under failures. Now I will hand it over back to Bharani to show how the data reaches CockroachDB.
Thanks, Vineet. Now let's look at CockroachDB, which is our primary OLTP database. Here are our tables, accounts, carriers, parcels, and scan events. We have applied regional by row partitioning, so data for each parcel or scan events is stored in the region where it belongs. This reduces cross-region latency and improves query performance. CockroachDB also replicates every piece of data. In our cluster, the replication factor is 7. So even if node fails, the system automatically elects a new leader and continues to operate without any manual intervention. And here in our metrics dashboard, you can see that the data ingestion is happening in real time. Because this is a free cluster, the write throughput is capped at around 5.50 transactions per second. So we can clearly see that the P90 and the P99 latencies increasing when our Kafka consumer push traffic is heavy. Now I will hand it over to Surya for a quick look at observability.
Thank you. For our observability layer, we use Prometheus to scrape metrics from Kafka, CockroachDB, and our FastAPI service, and we use Grafana to visualize everything in real time. Here you can see a sample dashboard. As part of the dashboard, you'll see one of our panels. That's the Kafka panel, where it shows the Kafka throughput. That is the rate at which the events are being consumed. And also, as we toggle through the dashboard, we can go to the API dashboard that shows the API error rate, that shows the API latency, that's the P95 latency, and even it has the latency heat map visualization. As we toggle through the dashboard, we can go to the system overview. We've created the system overview that tracks FastAPI and Kafka exporter services. It shows if they're running, it shows they're up. And this gives us a quick high-level overview of the entire pipeline. During scaling and fault tolerance tests, These visualizations helped us instantly spot spikes in the latency and measure how quickly the system recovered. Overall, this observability setup gave us a clear picture of performance and system health from end to end. Now, I'll pass it over to Harsh for the UI demo.
Before we move to the UI, I want to quickly add that the full scan event ingestion pipeline is now complete. Using the dynamic Python event generator, more than 12 million scan events have been successfully pushed through Kafka and ingested into CockroachDB. This confirms that our end-to-end ingestion design from batch production, Kafka distribution, idempotent consumer rights, and CockroachDB's geo-partitioning storage is working at real logistic scale. Now over to Harsh for the UI demonstration.
Thank you, Surya. So this is the UI which we built for tracking the packages, and to post and get the data from the database, we have created 5 different APIs for accounts, courier, parcel, scan, and tracking ID for getting the details of the tracking of the parcel. Let me just show you with the UI. So we have created 3 different pages in the UI. One is the admin panel, second log scan, and the track parcel. So admin panel gets the detail for the adding account, couriers, and the package details. Scannings get the details for the scanning events where the parcel is scanned, and the tracking events gets the tracking ID from the user to get the track of the packages. So now let me just enter a tracking ID. So now you can see the parcel's complete scan history pulled in real time from CockroachDB through our FastAPI backend. This completes the full flow from data generation to Kafka ingestion to CockroachDB storage to API to UI. So to conclude, GeoTrack brings together Kafka, CockroachDB, FastAPI, Prometheus, and Grafana to build a truly distributed fault-tolerant parcel tracking system. We demonstrated how system handles large-scale injection, how it scales horizontally, how it remains available during failures, and how geo-partitioning improves performance. Thank you.